All right, so we're going to try and put this into practice. So we're going to take a look at the integral over a region R of 2x minus y dA, where R is this region defined by four different lines. We've got y equals x over 2, y is x over 2 plus 2, and then y equals 4 minus x, and y equals 1 minus x. So I went ahead and drew all the lines on there. And one of the things we want to notice is that this region in terms of rectangular coordinates is not very nice. No matter how we choose to do it, whether we choose to do it vertically, so y being functions of x's, or horizontally, x is functions of y, we're going to have to split it into multiple regions, because when we take a look at trying to think about, all right, something like top curve, bottom curve. Well, we actually have lots of different sections that we would need, where if I take a look at top curve, bottom curve, well, I'd have to cut it here so that I go from this top curve to this bottom curve, and here to go from top curve to this bottom curve, and then again from this top curve to this bottom curve. So we would have to cut this into three regions in order to do it using rectangular coordinates. Doable, sure, but perhaps there's a better way. Now, one thing that kind of cues me in that doing a change of variables might be nice is what we actually have here is two different sets of parallel lines. So if I can find a way to kind of represent the line as a function of x and y, well, then really we'd be just going from a constant to a constant and then another constant to constant. So let's try and think about that for a minute. So let's take a look at like this first one. So we've got, well, y equals x minus 2. So if we think about it, like I said, if we're trying to kind of get them equal to constants, let's move that over. So y minus x over 2 equals 0. And then we might even go ahead then, we could adjust this, just if I don't want to deal with fractions, we could then make that something like 2y minus x equals 0, right? Just multiply everything by 2. Now, if I take a look at the next one, right, it's kind of comparative one, it's parallel line. We could do the same thing, move everything except a constant over, so y minus x over 2 equals 2. And then take a look at, well, now again, if I just clear out the denominator, I would have 2y minus x equals 4. Notice what we have then is this same expression showing up. 2y minus x goes to 0, and then 2y minus x goes to 4. So one of the things we're going to do then is we could say let a first variable like u be 2y minus x, because then u just goes from 0 to 4. It's a simplified version of that expression. Let's see if that works with the other ones. So also then try and take a look, let's add the x over, so y plus x equals, well, 4, and then y plus x equals 1. So we could then do let v be another variable in terms of x's and y's, where again I want v to go from something constant to constant. So if I let v be y plus x, then if I think about my region S, if S is in the UV plane, UV, well then U just goes from 0 to 4, and V goes from 1 to 4. So then we just get a rectangular region. U goes from 0 up to 4, and V goes from 1 up to 4. So we would have this rectangular region, which is much more simplified to put in an integral. Now though, what we're going to need to do is we're going to need to figure out, how do I adjust my integral? which means two different things. We have to find how to do x equals g of a function of u and v, y equals h of a function of u and v. So we have to find how do I replace x and y, and we have to find the Jacobian. Because the Jacobian is going to be that scale factor that helps me adjust that integral. So let's try and think about how to first find x and y. Well, let's start with some of these ideas that we have over here, right? We've got u is 2y minus x, and we've got v is y plus x. Our goal is to get a function for x and y in terms of u and v. So essentially to just rearrange these formulas, these functions, to try and get this to work. So what if maybe we start with trying to look for x, and we start with this one. So let's solve for x in terms of the others. So this would be x is v minus y. And then let's go ahead and take that and throw that into the top formula. So then the top formula says that u is 2y minus x. So this would be 2y minus v minus y. Notice what we're going to get here. We've got u is really 3y, right? 2y minus a negative y is 3y minus v. Then I can go ahead and solve for y. Notice I now have y as a function of u and v. So now we've got y is going to be, we'll add the v over, so we'll have u plus v, and then we have to divide by 3. So we have a 1/3 u plus v is y. We still need x, so this would be like my h of uv. So then we still need x. Well, now we could use either the other function, or we could use the one that we already solved for x, because now I know y. So then x is v minus y, which is v minus 1/3 u plus v. So then simplifying things there, we're going to get x is, well, we've got v minus 1/3 v, so we've got 2/3 v. And then we've got minus 1/3 u. So this would be my g function. So this is g of uv. Okay. So we're going to grab that guy. We still, remember, need to find the Jacobian. So let's work on finding that Jacobian over here. So we're doing the Jacobian of xy with respect to uv. So we need the partial of x with respect to u first. So x is 2/3 v minus 1/3 u. So we're going to get a negative 1/3 as the partial of x with respect to u. And the partial of x with respect to v is going to be 2/3. Partial of y with respect to u, really it's just 1/3 u plus 1/3 v, so really both of them are going to be 1/3. So then computing this determinant, we have negative 1/3 times 1/3 is going to be negative 1/9, and then we're going to subtract 2/3 times 1/3, which is going to be 2/9. So we really have -3/9 or -1/3 is our Jacobian. So now we're ready to put everything back into the integral. So my integral with respect to r of 2x minus y with respect to, let's say, x then y. Well, now we've got, well, x was, so we're going to have 2 times x we said was 2/3 v minus 1/3 u minus y, which y was 1/3 u plus v. Remember, we need to multiply that whole thing by the absolute value of the Jacobian, so the absolute value of 1/3. And then this is now going to be du dv, and we need bounds for u and v, but those were from over here. That was kind of how we picked u and v, was based on the bounds. So u went from 0 to 4, and v went from 1 to 4. So really what happened now is my integrand, yes, got somewhat more complicated, but not drastically. It's still perfectly reasonable to integrate. It's still just linear in terms of u and v. But my bounds became far simpler. I can just do a single integral, and they're just numeric bounds. So if we work on kind of cleaning all of that up, right, I really have 2/3 times 2/3 v was going to be 4/9 v minus that 2/3 times 1/3 is going to be minus 2/9 u, and then we have 1/3 times a -3rd is going to be -1/9 u, and then minus 1/9 v. We can combine those together. We might as well do it now. So we've got 4/9 v minus 1/9 is 3/9, which is just 1/3. And then we've got -2/9 minus 1/9 is -3/9, which is -1/3. So not bad. 1/3 v minus 1/3 u, that goes from 0 to 4 du, and 1 to 4 dv. And now it's a real simple integral to finish out. So I'll let you guys finish up that one. Right, v would go up to v squared, and we do 1/3 divided by another 2, so it would really be like a 6v squared. Well, sorry, actually that one would just give u first because we're doing the du first, so be more careful when you do your integrals than what I'm saying, but a fairly simple double integral to do at that point. But it would find me the integral from before of what we had. So this is a kind of nice first example to see kind of just how to get these different pieces in here. So don't forget the absolute value of that Jacobian. So even though it turned into a negative value, we switch it to an absolute value. In this case, it was a constant. Remember, like with polar coordinates, it's not always a constant. So we take a look at that guy. And then we'll kind of do more examples to see a little bit how we kind of pick those bounds for us. So our next example that we're going to do probably is just going to be on screencast, so we'll just watch the, we'll work it out on the page rather than on the board. And then what we need to do is just talk a little bit about, well, what about for triple integrals? How do we find those Jacobians?